My name is Landon Ellis, and I will be presenting extracting thermal diffusivity during high heat flux testing. I would first like to thank my mentors, Dr. Don Lipkin and Dr. Michael Dmitriev, for helping me throughout this project. An outline of the presentation includes an introduction, followed by the motivation behind this project, the numerical methods I used, and finally, research results and goals. Thermal diffusivity is a measure of how quickly heat propagates through a material. The goal of this project is to be able to extract a value for thermal diffusivity for an unknown material being tested in our lab. The first step to doing so is to analyze the heat equation for realistic boundary conditions. We will use the finite difference method to do this, which will then be modeled in MATLAB to show the thermal response of the material for the given boundary conditions. Then we will add a chop in the heat flux on the hot side, which will happen periodically, and will temporarily lower the temperature at the hot side, which will then be felt on the cold side and allow us to extract the thermal properties that we're looking for. We will then use these results to quantify how thermal diffusivity relates to the chop and heat flux. Like I said previously, the goal of this project is to extract a thermal diffusivity value for an unknown material during testing. This looks to be applied in the ultra-high heat flux facility that Texas A&M is building, and is also an extension upon the light flash analysis method. The light flash analysis method is a method to determine thermal diffusivity by heating one side of a sample with a quick pulse of energy and detecting the resulting temperature rise on the other side. We are looking to extend this method to include high heat flux conditions. This is the application of the finite difference method on the heat equation. The finite difference method is a numerical technique which approximates solutions to differential equations by discretizing them. We will apply this by dividing the spatial domain into discrete points and approximating the derivative with time differences. The resulting equations will be iteratively solved using MATLAB. As can be seen in the slide, the final equation, which gives us an update for the temperature at every internal node, can be seen at the bottom. Basically, this gives us a way to predict the temperature at all of the nodes within our sample that are not the boundary nodes. We now need to apply the finite difference method to our boundary conditions. We will first start with the hot side, z equals 0. The boundary conditions will have two parts to them. They will have a convective input and a radiative heat transfer from the surface, which will be due to the environment that our sample is in. The net heat flux can be given by the input minus this radiative loss. Using Fourier's law, we can then set our net heat flux equation and solve into the form of a fourth degree polynomial. We will then be able to, just like previously, iteratively solve this using MATLAB, which will help us model our thermal response. This gives us an equation that updates the temperature at the hot side over time. We can then apply the finite difference method to the cold side boundary condition at z equals n. This net heat flux will also have two components to it. We will have a convective input from our gas flame and a radiative transfer from the surface of our material to the environment that the sample is in. The net heat flux will then also be given by our input minus the radiative loss. We can apply Fourier's law of conduction to determine an equation that updates the temperature at this boundary for each time step. Rearranged into the form of a fourth degree polynomial, we can solve this in MATLAB and help model the temperature distribution within our sample. We are not testing a specific material in the simulation, but we chose a range of values that could be seen and tested in the lab. We are initially only going to change 3 of those values: thermal diffusivity, heat transfer coefficient, and the chop period. All the other material properties, as seen in this bottom table, will remain constant. We have chosen 2 different thermal diffusivity values, 2 different heat transfer coefficient values, and 2 chop periods. We have then arranged them to form 8 different test cases. We have chosen to vary these parameters because they will greatly affect the phase lag and temperature drop on the cold side and allow us for adjustment and extracting the measurements that we want. The first case can be seen in the plot above, where we start with an initially linear temperature distribution throughout our material. As the heat sources are applied, this will cause a rise in temperature and force the temperature distribution to change. It will eventually reach a steady state where the convective input and the radiative loss are balancing each other, which will cause the material to remain at a constant temperature and constant temperature distribution. Once it has reached this steady state, we will then start periodically interrupting the heat source. This will cause the hot side temperature to drop, and this drop will be felt throughout the whole material. It will propagate through the material and eventually to the hot side. We will only let the hot side temperature recover for a short amount of time before we chop it again. As seen in the 2 plots below, this is what causes the step-like graph. We are chopping the heat flux, letting it rise for a short amount of time before applying the chop. And as we can see from the cold side, those temperature drops are also felt with a slight delay on the cold side. This plot shows the previous data on a normalized plot. We are plotting the normalized temperature versus the Fourier number. The Fourier number is a dimensionless parameter that characterizes heat conduction. We use this so the results become more general and is easier to interpret. The temperature is normalized because it makes an easier comparison between the different data points, and it makes it easier to see how both sides respond to the same chop. The method that we use to apply the normalization is seen to the left. The Fourier number is equal to the thermal diffusivity times time divided by the thickness of the material squared. By measuring the material's response, this allows us to extract the thermal properties that we are looking for. This normalized plot makes it easier for us to see the phase shift that is happening between both of the chops. We can see that the red, which is the hot side, happens slightly before the cold side. This is because of the phase lag, which is the time that it takes that heat to travel through the material and be felt on the back side. We will see that the phase lag and the thermal diffusivity are related because of this. Here we are plotting 1 over phase lag versus thermal diffusivity and phase lag versus thermal diffusivity in order to verify the relation between phase lag and thermal diffusivity. Initially, the relation is seen in the equation phase lag equals L squared over alpha. This implies that phase lag and alpha, or thermal diffusivity, are inversely proportional. That is verified in the graph to the right, where we see as our thermal diffusivity value increases, so does our 1 over phase lag, and they increase at the same rate, giving us a linear plot. On the plot to the left, we are plotting phase lag versus thermal diffusivity, and we see that as the thermal diffusivity value increases, our phase lag starts to decrease. And as our thermal diffusivity value decreases, our phase lag increases. This implies that if we know the phase lag and can determine this value through our simulation of an unknown material, we can then in turn find the thermal diffusivity value related to that material. We now have a method to calculate the thermal diffusivity for an unknown material during high heat flux testing by relating it to the phase lag found in the simulation. The next steps for this research include to vary the parameters and material properties to further validate our experiment, as well as validate our results with experimentation from the lab and the data gathered in real life.